All right, in this video, we're going to take a look at some more examples of solving rational inequalities. So example 2c, we have x squared minus 3x minus 4 over x squared minus 4x plus 3. That expression is greater than or equal to 0. So here we have one where we have a 0 on the right-hand side, much like example 2a. So these are nice because we can set our numerator equal to 0 and set our denominator equal to 0 to find our critical values. So our numerator, x squared minus 3x minus 4, we can set that equal to 0. Same with our denominator of x squared minus 4x plus 3, we can set that equal to 0. Each one of these is nice because you can factor them. So the numerator factors as x minus 4 times x plus 1, and our denominator factors as x minus 3 times x minus 1. So setting each one of these as factors equal to 0 and solving them, we're going to get 4 critical values. We're going to get 4, -1, 3, and +1. So quite a bit to test out in this example. Now remember, our denominator values, the x equals 3 and the x equals 1, those are automatically open circles because they would cause the denominator to equal 0. Our numerator values, if we plug those in, we'll get 0 divided by something that's not 0, which is greater than or equal to 0. So our numerator values of 4 and -1 will make the original inequality true. Our denominator values of 3 and 1 would cause a 0 in the denominator, so those are automatically open circles. So closed circles for our numerator in this example, open circles for our denominator in every example. So now we got a little bit to test out. We need to test out a value in the original inequality that's less than -1, see if it makes this original inequality true. A value between -1 and 1, a value between 1 and 3, a value between 3 and 4, and a value bigger than 4. So quite a bit to test out here. When we do that, we see that the values less than -1 are okay, values between 1 and 3 are okay, and values greater than 4 are okay. So now we can just write the interval notation for this number line. We get -infinity, -1 with a bracket after -1. Remember, always a parenthesis before a negative infinity, always a parenthesis after a positive infinity. We're going to unite that with between 1 and 3 with parentheses there because of the open circles. And then unite that with greater than or equal to 4, which is bracket 4, comma, infinity, with, again, a parenthesis after infinity. From a visual standpoint, what we're asking here is where is the graph of the left-hand side at or above the graph on the right-hand side, y equals 0, which y equals 0 is the x-axis. So a graphing interpretation of this problem is where is the graph of the left-hand side at or above the x-axis? Well, it's at or above the x-axis for values of x that are less than -1. It's between 1 and 3 here, these vertical asymptotes, and also for values greater than or equal to 4. So again, looking at a visualization interpretation of graphs solving inequalities. All right, example 2, part D, we have x plus 2 over x minus 3 is less than 2x minus 2. So we're going to start with our denominator. X minus 3 equals 0 means x equals 3. So that's going to be an open circle because we do not want to plug in a 3 for x. That'll cause our denominator to equal 0. So now let's treat the original inequality like an equation. X plus 2 over x minus 3 equals 2x minus 2 or equals 2x minus 2 over 1. Again, we can multiply both sides by x minus 3 to clear out our fractions. You could also do the cross multiplication thing. So 2x minus 2 times x minus 3, we'll have to multiply that out, equals x plus 2. So when we multiply out 2x minus 2 times x minus 3, we get 2x squared minus 8x plus 6, still equal to x plus 2. We want to solve this polynomial by getting it equal to 0, and we've seen many techniques for what to do from there. So bringing over the x and bringing over the 2, we get 2x squared minus 9x plus 4 equals 0. And this is factorable. We could use quadratic formula on it. We could graph 2x squared minus 9x plus 4 and see where it hits the x-axis. Many different ways to do this, but we have x equals 1/2 and x equals 4. So we actually have 3 values here. We have x equals 3, which we know we're not allowed to have because it would cause the denominator to equal 0. We have x equals 1/2 and we have x equals 4. So our critical values then, we can use to set up our number line. We know the 3 because it would cause the denominator to equal 0. So I guess I got a little red alert here for making sure that 3 is an open circle. But for a half and 4, if we plug those in, we are not going to get a true statement because it's a less than here and not a less than or equal to. So we'll actually get for a half and 4, we'll get the left and right sides equal to each other. But because it's a less than symbol, they have to be open circles. So they're false statements. So testing out values less than a half, a value between a half and 3, between 3 and 4, and greater than 4. In the original inequality, we find that values between a half and 3 are good, and values bigger than 4 are good. So writing the interval notation for this, we get 1/2 to 3 with parentheses for the open circles. And then we're going to unite that with greater than 4, which is parenthesis 4, comma, infinity, and always a parenthesis after infinity. All right, so that about does it for this tutorial. Thanks for watching. I'll